Hello, this is Kevin. Welcome to my lecture on logical database design. I'm recording this lecture in the fall of 2021 for several of my courses, the most immediate of which is my course on database design and prototyping at the University of Illinois iSchool. But I'll be using it in other courses, and I'm going to be putting it out on YouTube. With just a warning for those of you who are not in my courses that the approach in this lecture is kind of tailored to what we're doing in my courses and the approach that we take in my courses. So, resources used in the lecture. The book that I primarily relied upon for the content in the lecture is a book that I use quite frequently in my courses. It's by Andy Oppel. It's called Data Modeling: A Beginner's Guide. And I'll just do a click through to the Amazon listing for the book, and you can buy a new paperback copy of it for less than $33. A good deal and a good book if you don't already have it. I've relied primarily on the content from chapter 6 of the Apple book. Okay? Okay. If we're going to do logical database design, we need to put it in some kind of context. Typically, people who are doing design of a relational database take a three-step approach. They begin with conceptual data modeling. Then they do logical database design. Then they do physical database design. So this is the middle step, okay? So if you're going to do a step like this, you have to pick the right starting point, okay? So here's my point of view on that. Start with conceptual data modeling, okay? Uh, you may have a lot of information already, and you may not have organized it into a conceptual data model. Okay, do that. Okay, so I have a lecture on conceptual data modeling, and if you haven't played that, well, that's the place to start. Another thing that people do that I'm not going to recommend is let's say they're designing a system. They might take the information from all of the designs that they've done for the user interface, all the report designs, all of the screen designs, all of the dialogue designs, and they might say, okay, I know we have to implement all these. Let's kind of turn these into data modeling parts, and then we'll start with logical database design. I think that's a mistake. Okay, because it's not going to be we're not going to be too far through the process. We're going to be down here in normalization. And you're just going to have a ton of work on your hands, and it's not going to be pretty work, and perhaps you're not going to do it all that well. Okay, so even if you already have of a designs for reports and screens and whatever, uh, take that and use that as a starting point for a conceptual data model. Do not um, skip that step and proceed ahead. I think you'll regret it. Okay? So that's the place to start. So let's say you have a conceptual data model. You've been following along with my course work. You created a conceptual data model. Are you ready to begin the steps of logical database design per se? I'm going to suggest that you're not quite ready to start because you maybe have some final improvements that you need to make in your conceptual data model. Okay? Uh, where would you get the information for that? Well, you have your latest version of the conceptual data model. Hopefully, you've reviewed it with the stakeholders um, who you've been working with as you created the data model. So, you're going to have some ideas from them about how maybe you came up a little bit short. Okay. And if you're like me, you've just been thinking about this for um, overnight, a day, a week, a month, okay? And ideas have been going through your head. Take the time to polish up the conceptual data model, okay? What kind of things could you improve about it? Well, maybe you have missing or incorrect entities on the data model. And when I say the data model, I mean as expressed in an entity relationship diagram in ERD. Okay. Are you missing any entities that you're going to need to support the system? Okay. Have you got any kind of incorrect? Have you called them the wrong thing? Or are they just a little bit wrong? Well, fix them right now before you start uh, logical database design. Okay. Same thing for the relationships. Okay. Take a hard look at the relationships and think, are these exactly right or are they almost right? And improve them. Okay. Um, take a look at the attributes. Uh, Typically, when we're doing conceptual data modeling, uh, we're going to, we're sure to get the most important attributes. But of course, um, in my scenario, the way I'm kind of painting it here, uh, we've done some thinking, we've done some talking to people. I'll bet you can think of some additional attributes that we forgot to include or that we got a little bit wrong. Well, tune them up, fix them. Okay. Uh, did we get the unique identifiers right, or are they a little bit wrong? Okay. Tune them up. And finally, if you've used supertypes and subtypes in your conceptual data model, and maybe you did use a supertype subtype relationship, and you've thought better of it, right? You have a relationship, but you've realized it's not really exactly a supertype subtype relationship. Well, redraw the diagram to make it a more conventional relationship. Okay. Um, the other way, maybe it's been kind of haunting you that one or more of the relationships on your diagram for your conceptual data model is really a supertype subtype relationship, and it didn't have the guts to draw it that way. Well, get some gumption and fix it. Okay. Now, I just want to point out that because you're changing the data model, once you're done and before you continue on with this, a process that we're talking about here, show it to your stakeholders one more time and make sure you haven't gone off on some kind of a tangent that they're not going to support. Okay. So what I'm really talking about is a final round of revision for your conceptual data model, including reviewing it with the stakeholders. Okay? Okay. So well, let's say that's done. And we have a conceptual data model that we're confident in. Okay? Um, Logical database design is primarily about a process that we call normalization. Okay, so let's talk about why we would want to do normalization. Okay, well, a normalized design eliminates redundant data facts from the database. Okay, and how does that help us? Well, one, if we have fewer facts, okay, if we don't have any facts that are in the database more than once, we're going to save space, okay? And historically, that was one of the major motivations for normalization, okay? When databases came into being years ago, the kind of storage that we use for databases, disk storage, was expensive. And in a typical IT shop, there wasn't a lot of it to be had. Well, that's really changed, you know. Um, so that's no longer really, whereas the cost of disk space was a major mo- motivator historically for eliminating redundant facts. It's probably not true any longer. The bigger motivation is um, trust in the database, trust in the data store. Okay? As soon as you have the possibility of having redundant data facts, you have the possibility that they're going to conflict with each other. And as soon as we have conflicting facts in the database, user confidence in the database erodes, at least in that part of the database. And you'll hear users say, well, we don't really rely on that because there's conflicting information there. So for for us, the major motivation for eliminating redundant facts in the database is going to be to maximize the trust that users have in the database. Okay? There's another aspect that's important as well, and this really goes back to the 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 sort of inventors and developers of relational databases, people like Cod. Cod identified three anomaly problems that you get in databases, relational databases, when you haven't normalized them. And that is the insert anomaly, the delete anomaly, and the update anomaly. Well, what are they? Well, typically, when circumstances change in the world outside that we're trying to model, we would like to be able to take one change in the outside world and have that correspond to one change in the database. Okay, so if we have uh, one more instance we find out in the real world, we'd like to come over and do one insert into the database. Likewise, if one thing should go away in the outside world, okay, well, we'd like to be able to come to the database and delete uh, uh, from, one of the entities, one of the tables in the database. And the same for the update. And one of the things that Cod found was if you didn't normalize the design, Okay, one change in the outside world would have to be implemented with two and three and four changes in the database, and they might conflict with each other, particularly when you're doing inserting and deleting. Okay, so the delete's really the big one that um, something has gone away in the outside world. We come to the database, we go to do a delete, and then we find out we're deleting facts about two or three things. Okay, and two or three things haven't gone away in the outside world, only one. Well, how did this come to happen? Well, we've combined things in an unhealthy way in the design in the database. So this problem in not having properly normalized the database uh, leads to these operational anomalies, right? And that's the other reason why we want to normalize the design. Okay. So I've mentioned a couple times already that we're doing this logical database design for a relational database. And it's probably true that uh, logical database designs are going to be specific to a particular technology. So when we pick the technology for the data store, um, there are several to choose from. Far and away, the most ubiquitous of these is relational databases. Okay, so that's the kind of logical database design that we're talking about here. Well, what other kind of data store technologies are there? Well, there are NoSQL databases. There are graph databases. Uh, there are these things called triple stores that are based on technologies like RDF and OWL. Okay, now the principles for those designs might be similar, but they won't be exactly the same as the logical database design that we're doing for a relational database. So the principles that we're talking about here apply in particular to the design for a relational database. Okay. All right. So we know that we're going to normalize. So what's that process look like? Well, I want to say that if you followed the advice that I've given you um, in my lecture for conceptual data model, we're already pretty well along. Okay, um, because um, if we've done a good job in creating our conceptual data model, it's probably not too denormalized, right? It probably has not got a lot of normalization problems. Okay, where do you get a lot of normalization problems? Well, as I mentioned earlier, uh, back here when we were talking about choosing the proper starting point. If you start with a well crafted conceptual data model and you follow the kind of advice that I give to practitioners in creating a conceptual data model, you won't have a lot of normalization problems when you begin the process here. If, on the other hand, you take an approach where you look at all of the all typically we call them views, all the views of the data that are implicit in the designs you have for reports and screens. If you begin there, okay? And you say, okay, I'm going to take each of the screens that I have and I'm going to express it as uh, a data model piece. And I'm going to take each of the reports that I have and I'm going to express it as a data model piece. I'm going to start there. Well, they're highly denormalized, okay? And so when you get to the normalization process, you have a boatload of work on your hands. Okay, so don't do that. There certainly are books that talk about taking that kind of approach. Okay, and in fact, the Andy Oppel book talks about how you would follow that kind of uh, uh, approach. Yet, um, it's not the way to go. And the reason it's not the way to go is that when you get to the normalization process, you just have a boatload of work on your hands that you don't want to be doing because it's not pleasant work. Okay? All right. So there we are there. So let's talk about what are we going to do for the normalization process. Well, I'm going to tell you that it's really the steps that I have listed here. Remove repeating elements. Okay, it's going to turn out that I call that do things the relational way. Turns out that relational databases don't have repeating elements. It's just not the relational way. Okay. Next, remove redundant attributes. Okay. Next, remove redundant relationships. Next, relocate misplaced attributes. Last, relocate misplaced relationships. Okay, so this list of things is if you go through these actions, you'll have taken the aspects of whatever data model you have that are not normalized, and you'll have cured them. Okay. Okay. So let's look at these one at a time. Let's look at remove repeating elements. Okay. What kind of repeating elements might we have in our data model? Okay. Well, if you followed my instructions for your conceptual data model, you've probably gotten rid of these already. Okay. You might have lists. Okay. So in one attribute, okay, you might have thought that you were going to have a list of things. Okay. That's not the relational way. That is not normalized. We don't have one attribute that has a list of things. Okay. Uh, you might have repeating attributes, because I'm attribute 1, attribute 2, attribute 3. Okay. Or you might have a repeating attribute group. So let's take a look at all three of these and see how we cure those problems. Okay? Okay. So what would a list look like? Well, the classic thing that people have done in designs that include having a list of as an attribute. Let's say that we want to keep track of, let me make this just a little bigger. Let's say that we want to track employees and the skills that they have. And by skills, I'm talking about, let's say this is a group of technical people. So what programming languages are they um, uh, qualified for? So the skills, it might be Python, Java, JavaScript, Perl, Rust, all those kinds of things. All right. Okay. So one approach, which is not the relational way, is to have a single attribute or column or field in the design, just called skills list or skills. And the intention is, we'll put them in Python, comma Java, comma JavaScript, not the relational way. Well, what is the relational way? Well, it's a two-table approach, okay? So we have the employee. It has a many-to-many relationship with skill, okay? And each of the skills are separate instances of the skill entity. So Python would be an instance of skill. Java, the same. Um, JavaScript, Rust, all the same. Okay. You'll notice that even though it's part of our work on logical database design, one of the things that we're going to do is we're going to take many-to-many relationships and we're going to implement them with an intervening associative table, because that's the last thing that I do in my lecture. I don't show that having happened yet. Also, one of the last things that we're going to do is we're going to turn IDs into primary keys, and we're going to add foreign keys. Well, I don't show that either, okay? When you're going to see that at the very end of the lecture, okay? So what we're concentrating on here is making sure that in our design, which is expressed as an entity relationship diagram, that we don't have any attributes that represent a list, okay? All the attributes should be things that get one individual value, okay? Now, what if instead of doing that in the design that you have a repeating attribute, okay? And so instead of just having skill list or skills list, you have skill 1, skill 2, skill 3. This is an old school kind of pre-relational approach. Well, that's not the relational way either. Repeating things are not the relational way, okay? Well, what is the relational way? Well, the same design that I showed you a minute ago, okay? It's we have an employee table and a skill table, and they have a many-to-many relationship, okay? That's the relational way. Okay. Repeating attribute group. Okay. So this is the same thing as skill 1, skill 2, but it's for more than one attribute. Typically, what we show for this is we have employees. For insurance purposes, we need to keep track of their dependents, right? Typically, we're going to have to keep track of more than one fact about the dependent. So the approach that we might take is having like, dependent 1 name, dependent 1 date of birth, dependent 2 name, dependent 2 date of birth. Okay, this is a repeating attribute group, okay? How do we solve this? Well, more tables. That's the relational way. So we don't have repeating groups of attributes. We would have an employee table. We would have a dependent table, okay? And the dependent table would have all of the attributes for the dependent, right? And there would be a one-to-many relationship between employee and dependent. Now, I'm just going to point out here that the relationship here has been drawn with a solid line, and the identifiers include the employee ID in forming the unique identifier for dependent. This is to indicate that dependent is a so-called weak entity. And how do I mean that? Well, it's pretty clear that we're not going to keep information about dependents for employees that we've deleted. Okay, so it shows a dependency. We're kind of overusing that term, but it shows a dependency between dependent and employee. Okay, this part of the design is maybe a little bit old school, but I just wanted to point out, if we ever want to say that the identity of one entity is dependent upon the identity of another, it's when we pulled out a repeating group from the primary entity. Okay? Alrighty. So, no repeating things in the design. Okay? Now, in the discussion of normalization that you see in the Andy Oppel book and in the typical book chapter on logical database design, they will talk about the need to be in what they call first normal form. Okay, and first normal form in everyday words is no repeating things. Do things a relational way. Okay? So once we have corrected all the repeating things that we might have in the design, well, the result is we've conformed with the rules for first normal form. Do things a relational way, no repeating things. Okay? Okay, now we also want to remove redundant attributes. Let's look at that. Okay, so we've got really two cases. We have situations in which we'll look at the data model as it currently exists, and there are redundant attributes in it. I mean, they're truly there. Okay, well, let's take a look at that. Okay, so here's a situation where we kind of made a rookie mistake. We have an order, item, a classic three table, kind of commerce or e-commerce design. Okay, and we have on the item, which could also be called the product, we have the name of the item and we have the list price. Okay, we have in a rookie design error, we've repeated the item name on order item, and we've repeated the list price on order item. And those of us who have been working with, say, relational databases realized we don't have to keep them here. Okay, we just have to join through to the item, and we can get the item name off of item, and we can get the list price off of item. And so we don't have to we don't have to put them here on order item. Okay, so that's what we mean by truly redundant attributes. So if we normalized it, how would we cure that? Well, because we already have item name and list price on item, we don't need to keep them on order item. We just remove them. So this is a truly redundant attribute. We made a modeling mistake. We get rid of it. Okay? We don't need it. Those of us who have worked with the relational databases, we realize that we don't need to keep things on order item that we can get by just joining item. Okay, so we made a rookie mistake, we fixed it. All right, so that's a truly redundant attribute. Okay, now we have other attributes that we may have included in the model that they are redundant because they could be derived. Okay, so let's look at that. Okay, so here's a design that has attributes included that could be derived. Okay, so let's look up here in the top version of the model. The easy one to see is an order item. Oh, I'm sorry, I've got this backwards. I had a version of this where these were swapped top and bottom. So the wrong version is on the bottom. Okay. So on order item, I have the quantity and I have the actual price. Now, a lot of times on invoices or reports, we'll have another column, extended price, which is just the quantity times the actual price. Okay. Some people, when they're doing the modeling, will copy that column right off the invoice and say, well, we're going to have an extended price in the data model. Because we can derive extended price simply by multiplying a quantity times actual price, we don't need to keep it, okay? Because we can derive it. So we only store the essential pieces of information, okay? So on the normalized version of this, we have quantity and actual price, but we've dropped extended price. Now, over here on the order, we're also keeping the total amount. So this is a total amount of the order. What is it? Okay, well, it is the sum of the extended price of all of the order items plus tax plus shipping. Okay, well, we can calculate that on the fly. Okay, we can do, those of you who've been in my database course realize that using a summary query, we can come up with the sum of the quantity times the actual price for all of the order items, and we could add it to tax amount, and we could add it to shipping amount, and we could calculate a column. We could have a formula for a column that would give us the total amount. Okay, so a normalized design doesn't include extended price, which is obvious, but it doesn't. It also doesn't include total amount because it can be derived as well. It's a little harder to do it. You need to do a summary query, but you can do it. So the normalized version, it doesn't include either extended price or total amount. Okay, so these were redundant attributes. Okay, so when we get rid of redundant attributes, we get rid of the truly redundant attributes, and we get rid of all attributes that we can derive. Okay? Okay, what about redundant relationships? Well, let's take a look at this. So again, this is something that I think is more obvious to people who are learning about design, who have been involved in using well-designed relational databases in the first part of a database course. Okay, so Here I'm showing a problematic design on top that has a redundant relationship. So we have a customer has an order. Each order has uh, uh, really one-to-many order items. That connects to item. That connects to category. These are categories um, of products, right? And in this design, the designer has said, "Oh, well, I might want to ask uh, for each customer, how much have they bought from each of the categories?" Okay, so I'm probably going to want to connect customer directly to category. And anybody who's been in kind of around relational databases long enough realizes that this is a redundant relationship. If we want to find out how much a customer has purchased from each of the categories, we join customer to order item to category. Okay, so we don't need this redundant relationship. Uh, why don't we just want to add it for efficiency or something like that? Well, because it's a redundant fact in the database. So relationships are as much a fact, they're a first class fact in the database. They're a full opportunity to contradict the other fact. All right, so we don't want this. So when we get rid of it, we have the classic design that doesn't include the redundant relationship. So attributes can be redundant because that's one way to model a data fact, and relationships can be redundant as well because even though designers don't really feel it in their true heart of hearts in the beginning, relationships are just as big, just as important, just as first class of a fact as attributes are. And they can be just as easily redundant. So we don't do things like we see on the top part of the slide. Okay, we do things on the bottom. So that's how we eliminate redundant relationships. Okay, a telltale sign of a redundant relationship is you start to see a circuit. Okay, uh, designs that include a circuit like this are suspicious. Now, in my database design and prototyping course, we do have a couple of databases that we work with that appear to have a circuit because, oh, we've got facts in two different contexts. We've got facts in kind of historical context, and then we have some default values which are really in a prospective context. So it's possible to look at a diagram and see a circuit and go, oh, well, that's really suspicious. And you can realize that these facts are not exactly the same fact, and you don't have a duplicate, you don't have a redundant relationship on your hands. But I would say that as soon as you see a circuit, you have to start the inquiry. Is this a redundant relationship, or possibly are these facts used in different contexts such that they're not precisely the same facts and they're not precisely redundant? Okay. All right, so we've done the first three. We've got two more left. Relocate misplaced attributes. Let's look at that. How does that look? Okay. So here's a classic thing that you'll see where people have just placed the attribute or group of attributes on the wrong entity. Okay, so here's a case where we have employees, and each employee is assigned to one and only one facility. Oh, that's an office or a factory or a store, right? Okay. So here's what we've done. We've decided that each employee is going to have a work address. Okay, and so we're going to have work street address 1, street address 2, city, state, and zip. Okay? The problem is that the work address is really the address of the facility where they work. Okay? And so you can kind of think of it as belonging to the employee, but in fact it belongs to the facility. So if we properly place these, we have an employee, no work address, is assigned to a facility, and the facility has the address, street address 1, street address 2, city, state, zip. Now, how does that help us? Well, the problem in the top design with the misplaced attributes is that let's say that we have a facility that's a factory, okay, and let's say we have 1,000 employees who work at the factory. Yeah, so we run 3 shifts a day. Yeah, 3 shifts a day. 333 people. One shift has 334 people. Okay, and we put the same address onto 1,000 employees. Okay, let's say we relocate that factory. Okay, let's say we move it down the street. Okay, it's kind of aging. We redevelop it, new technology. Let's say we're good to the employees. We include a health club and a daycare and better dining facilities and maybe better medical facilities. Let's say we move the HMO there too. Okay, so everybody's excited that we're moving to the new facility. Okay, how many things are we going to have to change in the database? In design 1, we're going to have to change 1,000 addresses. In a properly normalized design, where we have placed the attribute on the right entity, we have to change 1 address. Okay, that makes a lot more sense. All right? Okay, so that was misplaced attributes. So, because of the fact that attributes and relationships are the same kind of facts, just expressed in different ways, and they're both first-class facts, in the same sense that you could misplace an attribute and put it on the wrong entity, you can equally do the same thing with relationships. What would that look like? Well, here's a classic, okay? This one comes from the air travel industry. Okay, so here, let's make that one smaller. Okay, so here's the situation. We're in the database. We're keeping information related to airline flights, reservations, and passengers. Okay, so we have the flight, we have the reservation, we have the passenger. And it turns out that the flight, the reservation, and the passenger is this a classic 3-table, many-to-many relationship that has, or 3-entity, many-to-many relationship that has an associative entity in the middle that carries data, right? Okay, let's say that we want to be able to print on the ticket, or we want to be able to put up on um, the display at the gate. Okay, let's say we want to say what kind of aircraft we're flying that day. Okay, so let's say it says, we want to say uh, Boeing 787, or we just want to say 787 Dreamliner. Okay, well, where's that going to come from? All right. Well, here's what we decided to do. We're going to have a lookup uh, entity to control the values of the aircraft type. So we're going to have a relationship between flight and aircraft type, and we're uh, and so the aircraft type for that flight is going to be 787 Dreamliner. Okay, fine. Is that where it really belongs? Now, I want to say that each flight uses a particular aircraft, and the aircraft has a number of facts associated with it, represented as either attributes or relationship. And I want to say, in showing you the design at the bottom, that this has aircraft type relationship really belongs to the aircraft. Okay, so a particular flight is going to use a particular aircraft, okay, and it's the aircraft that has an aircraft type, okay. So, for instance, um, um, well, it just gets things, it's just misplaced, okay. It says misplaced if you're using a relationship is if you had put the attribute on the wrong entity. So having the relationship connected to the wrong entity is really just another way to put the attribute on the wrong entity. And here's where you begin to see that attributes and relationships are really just two different ways to express a fact. They're both first class facts in the database. So if you can get the attribute on the wrong entity, you can easily put the relationship connected to the wrong entity. Okay? And the relationship in the top version is misplaced, and the relationship in the bottom version is properly placed. So let's talk just a little bit about the normalization process and normal forms. Okay. Um, Often when you see this, it discussed, and I mentioned the Andy Apple book, and particularly chapter 6 from the Andy Apple book a little bit earlier. But typically, when you discuss the normalization process, um, classic data modeling folks, I talk about these normal forms. Okay. And the normal forms are kind of like degrees of goodness in the design of the relational database. Okay. And every time you go up a level, you go from first normal form to second normal form to third normal form, and we go beyond that. There's fourth, there's Boyce Codd normal form. There's all these normal forms. Okay. Um, and some of them I think are discussed in Andy Apple's chapter 7. Now, typically for the kind of databases that we learn about in my course, which are uh, online transaction processing databases. These are the databases that enable um, day-to-day operational systems for the organization. They keep the day-to-day facts of the organization. I'll contrast them with data warehousing, information center, data analytics databases, right? Okay, so generally speaking, the latter, those data warehousing analytical databases, are denormalized. Why do we denormalize them? It speeds them up. Why doesn't that create a problem that they have, potential contradictions in them? Well, the fact is that we rebuild them all the time. And what do we rebuild them from? Well, these online transaction processing normalized databases. Okay. So we're designing the normalized ones. Okay. Typically, we tell the designer, like you, that you should be normalizing these to third normal form. Okay. If you look at the actions that I have you doing here, these will get you to third normal form. Okay, that's usually the goal for people who design these kinds of databases. Okay, now there's usually a lot of discussion in the data modeling books, including the Andy Apple book, of what's the difference between a violation of first normal form and second normal form? Or what's the difference between a violation of second normal form and third normal form? Okay. I personally have never found these helpful. Okay. Uh, the the problem that I have is that it's really focusing on the wrong thing. Okay. You'll hear people complain about Western medicine that it's very disease and diagnosis oriented. It's not wellness oriented. Okay, so there's a lot of focus in Western medicine in having, sort of a taxonomy in all the diseases and knowing exactly how they're different. Okay. And then there's another approach, and you could call that the Eastern approach or the wellness approach or the holistic approach or the hippie approach. You could call it whatever you want, that kind of focuses on wellness. Well, the problem that I see in trying to characterize the difference between first, well, in particular, second normal form and third in normal form, that you look at some kind of a problem that you have in your design and say, is that a violation of second normal form or third normal form? Well, it's not well. Okay. So, and I'll tell you personally, it's hard for me to decide when I see a problem. If you look at all the problems that we just had, and you were to quiz me, is that a violation of second normal form or third? I'd probably get some answers wrong. Okay. But I can tell you how to design it the right way. Okay. So I think that the discussion about exactly which of the normal forms you're violating is not a good discussion. Okay, you can disagree with me. You can like that discussion in the Andy Apple book or any other book. Okay, if you find that helpful, gosh, please concentrate on it because it works for you. But for my purposes, and I think for the beginner data modeler in general, okay, we just want to be sure that we don't leave anything behind that doesn't make it to this third normal form normalization. And if we do each of these things that I've listed here, remove repeating elements, remove redundant attributes, remove redundant relationship, relocate misplaced attributes, relocate misplaced relationships. If we do those, in that order, in some other order, if we do all of those things, we're going to wind up with a design that is normalized to third normal form, and then we're done. Okay? So I suggest that you think of it that way. If you want to think about it in a more complicated, diagnostic way, well, I think there's a lot for you to read. And if you find it helpful, I think that's great. Okay, are we done yet? No, we're not done yet, because we need to make a couple of more changes in the design, in our ERD, in order to fully adapt it to being a design for a relational database. Okay, so let's go take a look at that. So the three things that we need to do are resolve many-to-many relationships, convert unique identifiers to primary keys. That's pretty easy to do. And add foreign key attributes. So let's look at each of those in turn. Okay, resolve many-to-many relationships. Let's look at this. So in conceptual data models, well, first of all, at least in theory, you can create a conceptual data model, and then you can go off and implement it with a lot of alternative technologies. One of them is relational databases. Okay, so we're currently learning how to do the logical database design for a conceptual data model that we have decided to implement with a relational database. Okay, we could have decided to go ahead and use a NoSQL database. That would have been a different logical database design. We could have decided to use a graph database. That would be different yet again. We could have decided to use a technology called a triple store with components like RDF and OWL. That would be different yet again. Okay, so what we're talking about here is how do we adapt the design for a relational database? And in conceptual data models, they have high magic, okay? And you can just draw a many-to-many relationship like this. As long as it's not carrying any data, it's fine to just draw it as a line, okay? But when you come down to a logical database designed for a relational database, relational databases are not able to implement many-to-many relationships directly. Some of the other technologies that I talked about can implement them directly. Okay? So if we're going to do a logical database design for a relational database, we need to insert an entity, which will eventually become a table in our physical design. We need to insert an associative or linking or intersection entity. All right, let's look at that. Okay, so what does it look like? Well, because it's just implementing the relationship, okay, it needs to connect these two. Now, the simplest way to do this is to have the identifier, which in our next step is going to become our primary key, have it become the combination of the unique identifiers from the two entities that we're trying to connect to each other in the many-to-many relationship. Okay, so this is a classic design. We insert an entity in the middle. Okay, what was a many-to-many becomes a one-to-many on each side of this intervening table and intervening entity, I guess. In logical database design, we still call them entities if we're being very technical, right? So this is an associative entity or a linking entity, okay? And the way this gets implemented is that the many side is always up against the entity in the middle, okay? Why is that? Well, it's just what works. When you take a many-to-many and you implement it with an associative or linking entity in the middle, you get a one-to-many on each side of that, and the many side is always up against the associative entity. It's just the way it works. All right? Okay. You'll see that we've got solid lines on each of these. And typically, when you're using the notation that we're using, if we have a solid line, it just indicates that the identifiers that we're using for the associative entity have been borrowed from the two primary entities. Okay? Now, if we gave this an identifier of its own, which I often do, okay, well then the solid lines would go away and we would have a dash line on either side. Okay. How do we decide to give it an identifier of its own or not? It's usually a question of how many of these we can have. If each user is only given permission to play each role one time, if it doesn't make any sense to give them that role, that permission 2 times or 3 times or 4 times, then the design that we have here is perfectly adequate. Okay, if this were a different design, if these were like if these were like employees who volunteered to do some activity, and you could volunteer more than once. Okay, well then we probably would want to give this volunteer entity its own ID so that it would be possible to have more than one instance of the relationship. You'll also see that we don't have names on the relationship on either side of the associative entity. Some people put them there. I think it's a waste of names because we typically name this entity approximately the same thing that we would have named the relationship. Okay, so this entity has just become the embodiment of the relationship, and it takes on approximately the same name, has a permission, has become permission, and you don't really need to name these. As soon as you see a design like this in your head, the light should be going on. Oh, this is a many-to-many that we have implemented with an associative entity. Okay, so that's what's going on there. That's how we resolve many-to-many relationships. Are we done yet? No, got a couple more things to do. Convert the unique identifiers to primary keys. That's pretty easy to do, okay? All we do is we go to the model and we take every attribute that said ID and we change it to PK for a primary key. Why do we do that? Well, we've chosen a technology, okay? We've chosen relational databases. Identifiers in relational databases have a special name. They're primary keys. So if these are single attribute primary keys, they just say PK right in front of them. If there are, if in fact we have a primary key that has more than one part, well, we have PK in front of all the attributes that make up the primary key. Okay? The trend in relational database design is to have fewer and fewer entities or tables that have compound primary keys. More and more you'll see that tables have one simple integer key, right? So I know that I just showed back here and we were resolving many-to-many this associative table that had a two-part ID, which would have become a compound primary key. What a lot of people are doing is just giving it its own ID, not borrowing the identity from the neighbors, and they're even giving entities or tables like this simple integer keys, right? This is probably the only kind of table that I will have a compound primary key on in my database. And sometimes not even that. Okay? All right. Are we done yet? No, we need to add foreign key attributes. Okay, well, let's look at this. Okay, now why haven't we added foreign key attributes before? Well, because we started with a conceptual data model. Conceptual data models can be implemented with a lot of competing data store technologies, and only relational databases or data store technologies that in which the relationships are implemented with foreign keys. Okay, so how do foreign keys work? Well, each table has a primary key. Okay, that's how you point to instances. Each entity has a primary key. That's how you point to instances. So when they become a table, when we get to the physical implementation step, an instance is a row. How do you point to a row? Well, you point to it with a foreign key. Okay, so here's what you do. You take the same attribute that is the primary key of the primary key table, and you copy it over and you put it on the foreign key table, and you make it a foreign key. Sorry about that. Got interrupted. Okay, so the foreign keys go on one side of the relationship. How do you figure out what side? Well, you know what? They always go on the many side. Okay, so most relationships are one-to-many. So we have here, we've got a one-to-many, we've got a one-to-many, we've got a one-to-many, we've got a one-to-many. Okay? If you have a one-to-many, the foreign key is always on the many side. Okay? Now, when you really think about this, it's not really possible for them to be on the one side because a foreign key can only point to one thing. Okay, so it wouldn't really be feasible to put a key on the one side and have it to point to all the instances on the many side. Just would not mechanically work. Okay, so if you have a one-to-many, it's always on the many side. What if you have a one-to-one? Well, you might remember from conceptual data modeling, I told you always be suspicious of one-to-ones. Okay, but if you have a one-to-one, pick any side, but only put it on one side. Okay, we don't point both ways. Okay, why don't we need to point both ways? Well, when we get to the physical implementation of relational databases, we're going to find out that every foreign key has an index. Okay, and that foreign key index allows the database server to travel across relationships in both directions. Okay, so even though we're only pointing from the many table to the one, okay, because we have a foreign key index that's associated with the relationship, and because we always have a primary key index for the table with the primary key, we have indexes that work in both directions. And that's the reason why we don't need to point in both directions. We don't need to do it on many-to-manys, and we don't need to do it on one-to-ones. So if you have a one-to-one, and again, you should be suspicious of one-to-ones, but we do have them. But if you have a one-to-one, pick a side. Okay? Don't implement it on both sides. Pick a side. All right. That's it. Okay? Now when you've done this, you have a normalized a data model that's been adapted for relational databases. We've resolved all the many-to-manys. We've identified the primary keys, and we've added the foreign keys. And we're ready to go on to the next step, which for a relational database is to do the physical database design and create the schema. Okay? All right, that's it. I'm going to say bye until next time. Bye-bye.